Good Saturday afternoon, everybody. As Irakli perfectly mentioned, I'm Hrant, and today we're going to talk about explainable AI. So most of the time, we will concentrate on the good side of the explainable AI, but we will not forget about the bad and the ugly as well. So let's go on. Today's agenda is we're going to have a bit of background and motivation to the explainable AI, why it is important to, what is explainable AI and why it is important to actually have AI explainable and interpretable. And then we're going to concentrate on the taxonomy of explanations, what type of explanations we have, what is the ecosystem, what are the existing solutions to the ecosystem. And we're going to also speak about the bad and the ugly, the drawbacks of explainable AI, and the ugly part is when we come to the causality issue. I'm Hrant Davtyan, and I'm an economist by background. Actually, I've been living in Tbilisi for years, so I'm an Armenian, but one of my master's degrees I received from ISET, International School of Economics in Tbilisi. So I'm an economist by background and very well familiar with Tbilisi as well. Right now, I'm running Metric, which is a data science consulting company and also AI product development company. We have our own products and we have quite large portfolio of consultancy expertise. I'm also teaching at the American University of Armenia courses related to data science. So at Metric, we are doing like different stuff related to data science. We are dealing with financial data, cryptocurrencies. We are dealing with taxation data. We are dealing with judicial system data. We are dealing with live data from web cameras, and we have developed a lot of different products for our customers. For example, we have a product which is doing lie detection. When a person is speaking to the camera, we are able to, on a real-time basis, detect whether he or she is lying or not. And we have some other things, but among all, we have our own products, which we call TabuLearn. So TabuLearn is an after-ML solution, which is like a one-click solution that develops the machine learning model and provides full explanations. You just need to provide the data and provide the target variable, and it will automatically create and engineer a lot of features, develop AI model, and most importantly, explain them. Okay, so this is interesting because we have different products, but right now I'm drawing your attention to TabuLearn because it's the only one which has this explanation component among our products. Okay, so explainable AI is nowadays a very, very important topic, and many people are trying to develop products related to explainable AI. Many people are trying to do research in the field of explainable AI, and many people call 2020 even the year for explainable AI. So let's see what is this explainable AI and why it is important. Nowadays, artificial intelligence is everywhere. Okay, it penetrated all the sectors and all the fields of the industry. We can have AI models working in the retail. We can have AI models in the healthcare. We can have AI models in construction even. For example, in healthcare, AI models are diagnosing patients. In telecommunication sectors, they are trying to understand the reasons behind telecommunication network failure. In automobile industry, we have the self-driving cars by Tesla and others. In the retail, AIs are used to, let's say, predict the customer churn or provide recommendations. So there are many, many applications and use cases of AI in different industries. And I think I will be even correct to say that AI has already penetrated all the industries out there. And because this is so important, because it is used in all the industries, so we are trying to have artificial intelligence models that are as accurate as possible. So they're making the best possible predictions, and we're spending our time to train and improve the models as much as we can so that we end up having the most accurate results in the end. But the problem with accuracy is that there's always a trade-off, okay? Together with higher accuracy comes lower interpretability. I will explain later on what I mean by interpretability, but in general, assume that interpretability is how much you can understand what's going on behind the model. Okay, so in this simple graph, you can see a lot of models, most of them very well-known models, and the graph shows that whenever we go to the right-hand side and we apply more and more complex models like deep neural networks, most of the time, it's not like 100% correct, but most of the time we end up having higher accuracy. There is a trade-off because we end up having a better model, which is less and less interpretable. So even so, we end up having better results in the end. They are not able to understand what's going on in behind. In general, people call this black box versus white box problem. These complex algorithms that have a lot of complex mathematics in behind and are trying to capture some patterns in the data that the human being may not be able to capture, like deep neural networks, for example, many times are called black box algorithms because you provide the data as an input and then you don't know what's going on there. Of course, you know the mathematics, but you know the calculations, but in terms of business insight, you don't really know what's going on inside the box. You just provide the data and you get the output, the prediction. On the left-hand side, we have these white box models that are fully transparent, which means you perfectly know most of the time why a certain prediction was made by your algorithm. The question is, should we use white box models or black box models? Because the thing is, the black box models usually provide much higher accuracy, but we don't know what's going on. And the white box models, which explain what's going on, do not really provide us that much high accuracy. Okay? So explainable AI comes in here. Explainable AI is the field of AI, which is basically researching models and techniques that help human experts to understand the outcome of a prediction done by AI algorithm. So if an AI algorithm is making some prediction, explainable AI is trying to explain why this prediction was made. There are two terms that are usually used interchangeably. They're very similar, so it's okay to kind of use them as synonyms, but scientifically they will be different. So there is no clear-cut definition for me to provide, but in general, explainability means answering the question why. If you have an AI algorithm and it is making some predictions, you want to understand why your model gave a certain prediction. If you know why, then you're able to explain. So explainability is when you're able to understand, when you're able to get the answer to the question why. Interpretability, which is very related to explainability, is a bit different. It is actually trying to answer the question, what if? So you're not just saying why this certain prediction is happening. Instead, you're trying to see what will happen if you change the inputs. If we go for the customer's case for the supermarket chain, for example, explainability for the problem of predicting customer churn, the fact that your customers are not buying from you anymore, will be when you say, okay, my algorithm is saying that this customer will churn in future, will not buy anymore because he's not satisfied. Interpretability will say, okay, what if I increase his satisfaction? What if I invest more money and provide him some discounts or bonuses? Will he stay or not? So explainability explains why he will leave, and interpretability helps you to understand what if you change some stuff? What if you make investment? What if you change the inputs? Will actually he change his decision or not? Some questions that you may ask for AI, which the black box algorithm will not be able to answer unless they are explained, are why the algorithm predicts a certain output. For example, if you have a model which is predicting whether your employees will stay or leave your company, but why your algorithm is saying that some employee, let's say Jon Snow, will actually leave? What was the reason behind this prediction? Why does not he predict that Jon Snow will stay? If it is making some predictions that are wrong and some predictions that are correct, which is the case with AI, it's never fully correct. In which cases your AI is correct? If it is fully black box model, you don't know in which cases it's correct because you don't really know what are the relationship and pattern it found in the data. What's wrong with your AI model? Why it is actually making wrong or correct predictions? When can you trust the AI model and when can you actually apply it in production? And how can you improve it? All of those are questions that are, if asked to black box model, will not be answered unless you use explainable techniques. Let's go on and understand in more details why explainability is important. There are many, many reasons, but number one reason, which the others are actually connected to, is trust. We, as a human being, want to trust. We want to trust the decisions made by our algorithms or about us. For example, when we go to the doctor and we have a headache, we go and tell the doctor, dear doctor, I have a headache. What should I do? And doctor gives us, I don't know, some pills and the headache goes off. Of course, we're satisfied with the solution because the headache went off, but we're also curious as a human being. We want to understand why we had the headache, right? So at least and I assume most of you would probably ask the doctor why I have a headache. So they're not satisfied just having the solution. We want to have the reasons behind this solution. We want to understand why the doctor came to the solution, why we had the problem in the first place. So when we go to the doctor, we just don't say, give us the solution to get rid of headache. We say, why do I have a headache? because you want to trust the solution. And assume you have an AI algorithm, and instead of going to doctor, you open a website which has perfectly accurate, like 99% accurate algorithm that is telling you, you have to take this pill and you will not have any problems anymore. Would you really take the pill unless you understand the explanations behind the decision? I don't think so. Even if it is fully accurate, you would try to understand why it is telling you to take this pill so that you can trust it. So trust is the main issue when it comes to AI, and unless you trust, you will not be really able to take your algorithm to production. Explainable AI helps you to explain the algorithm, helps you to explain the model so that you can trust the predictions of the model. The next problem is regulation. So some regulations just enforce directly to have explanations. For example, I'm not really expert in these legal issues, but we have heard about GDPR, right? So the General Data Protection Regulation. And if you're working on the GDPR, there's a statement which says basically that if you are releasing to production an AI model which is directly making autonomous decision about a human, and this human has the human right to ask explanation for the decision. So if you're using AI model in your business to make a decision about a human being, then human can come to you and ask for explanation. He has the right to do so, and this is like a regulation that you have to satisfy, which means you cannot really have an AI model which is fully black box and no explanation at all. So the second reason why you may want to have explainable AI is because you just have to, okay? Whether you want or you don't want, you just have to have it. Of course, in some cases, regulations are kind of vice versa. In some cases, you don't want to have explainable AI because if people know what's going on inside your algorithms, they may be able to manipulate it. Some examples are in case of taxation. If you tell the companies what is your strategy to audit as a tax authority, and they know your algorithms, they know that you're gonna audit this company on this day, and then probably they will take the measures to hide all the inconsistencies in their paperwork of the tax reports. But if they don't know if it is unexpected, they may not be able to do so. So in some cases, you may even want to have black box algorithm in terms of regulations, but many times regulations enforce you to have explanations. The third reason is insight. In many cases, you want to have explainable AI because you want to have insight. What's going on? You want to understand the reason behind to take an action. So you want to have actionable insight. Let me bring an example. Right now, we are working with a company which is providing these cable network services to telecommunication providers. They're very huge. They have like a huge network, and it's like when you have the modem in your house, and sometimes they're having problems with your modem, with your internet connection. Like most of the Armenians nowadays who are using UCOM have problem with internet connection for some reason. So this company that we are working with is able to understand when the modems are actually healthy, when they are working or not. So they don't really need AI to predict whether modems are healthy or not. But they approached to work with us to understand the cases, the reasons behind unhealthiness of the modem. So even so they can make the perfect prediction or almost perfect predictions, they don't need AI for that. They need AI to understand the reasons, to explain the reasons behind modems not working, behind modems actually slowing down, behind internet connection being lost, behind the television network lagging behind, and things like that. So in some cases, when you're using AI, your objective is not just to make a prediction, but instead to have the root causes of that prediction, to have explanation of the prediction, so that you can find an actionable insight that you can take, and that you can take some action and then improve your business. Another example will be customer churn. Like you can have an AI model that predicts whether your customers will stay or your customers will churn. You would probably also like to understand why your customers stay. Who are the customers that churn? Which segment is that? Why do they churn? What can you do to stop the churn? What actions can you take? If you don't answer these questions, then okay, you have a good model which is making a prediction, but it doesn't really help you to take any action to improve your business. So explanation can be very important for business in terms of taking the future actions. And the last thing is improvement. No AI algorithm is actually perfect. Even if you go to the face detection, face verification field, people are still researching it to improve the face verification algorithm because they are not perfect. I mean, iPhone has this automatic face unlock. When you look at the iPhone, it is unlocking if it sees your face and recognizes it, but still people are researching to improve this algorithm. So no algorithm is perfect. And you can, of course, improve algorithm without understanding what's going on behind. You can, for example, provide more data to your algorithm. You can try other models. You can try to tune your algorithms, but you will be better off if you really understand where your algorithm makes mistake and you concentrate all your powers or your strengths to actually solve these problems. So whenever your algorithm is making a mistake, you would be actually better off to try, instead of just like wildly going off and trying to improve your algorithm, try to actually improve it in the places when the algorithm is making mistake. Is it is it because of gender of your customers? Is it because of age? Is it because of other demographic measure? Or is it because of financials? So what's the problem with your algorithm? Why it is making error? When it is making error? Unless you have answers to these questions, you wouldn't really be able to go on and improve your algorithm very much. So improvement is another reason why you may want to actually have explainable AI. So as we discussed, four things, trust in AI is number one reason, and the others are really related to that. Second is regulation. Third one is actionable insight or just an insight. And the last one is improvement. So based on these four principles, you really want most of the time, and many times businesses are interested, to really be able to explain the predictions behind their algorithms. If these four things were not enough to motivate you that explainable AI is something important, then let's go on and take a look some drawbacks and some problems of AI. Like this is a typical AI task, right? Face verification. And the face verification task turns out can easily be fooled if instead of the live human, you just show a photo. If you search for Google, you will see that there are lots of cases when people were able to fool the face verification algorithm, even the ones in the border cameras, by just using 3D masks or photos. Okay, so for example, your iPhone is unlocking whenever it sees your face. So you can take the iPhone of, let's say, your friend. If it is not really working perfectly, then you can take the iPhone of your friend, theoretically, I'm not encouraging to do so, show his ID or her ID, and it may unlock. So if you show a photo and AI algorithm unlocks, then basically it is failing, right? Because you were able to fool AI. The reason you are able to do that is because you train the AI algorithm, you develop your model on images. You develop your model on images, and now it is working on live face. It's excellent that the model works on live face, but because you developed on images, it will also work on images. So what you want is that AI algorithm works on face, but not on images. This problem is very well-known problem in the face verification field, and there are very well-known solutions. One is the liveliness check. So people try to check the liveliness instead of just having an algorithm which is predicting whether this is, I don't know, Hrant or not, just because he has these eyes, these nose, these ears, and so on and so far. They are trying to see, is Hrant like in a picture, or he is alive? So is he closing and opening his eyes? Is he moving his face muscles and stuff like that? Because as you can see, pictures cannot really move the muscles unless it is the pictures from the Harry Potter movie. So you cannot really have pictures moving, right? That's why whenever you want to have face verification problem, you better have liveness check. This is a well-known problem, but you wouldn't really know about this if A, you didn't experiment it, or B, you didn't explain it. If you explain the algorithm, you would be able to see that the algorithm identified this guy because of the, let's say, distance between his eyes. So it's very unique, very individualistic about him. Nobody else in the world, just a simple example, has this distance between eyes, pupils. That's why he was considered this guy. So if you're able to go back to these explanations and understand the reason why your algorithm makes this prediction, then you will understand that there are cases that you haven't observed yet. That's why your algorithm is perfect. But in future, you will have cases that it will be fooled. Okay. Another perfect example is by a system called recognition by Amazon. So the large, big Amazon. Okay, so there's a system by Amazon which is said to have misclassified these 25 famous people. To say the truth, I don't know these people myself, many of them. Well, I know some of them, but I know many. I don't know many of them. So it says that these people are very famous sportsmen, and Amazon misclassified them as felons. Okay, Amazon misclassified them as felons. Unless you go back and understand why Amazon made this mistake, you wouldn't really be able to solve this issue, because in future, it may not misclassify footballers as felons, it may misclassify actors as felons. So you really have to go back and explain what your algorithm is making the prediction based on. If you know what features are the reason your algorithm is making this or that prediction, you will be able to beforehand expect the possible mistakes and errors and take care of them, unless your model goes into experimentation or production. There are many other famous examples which we don't have enough time to cover. Some examples are, for example, by Google Translate, which is again using this AutoML black box models for translation. And many times you can see that Google Translate is actually doing some not very smart translations. If you go back and explain why Google Translate is making these translations, you will be able to actually improve them. You will be able to understand, okay, so that's okay, I made the wrong translation, but it's because I had this typo in my word. It means I should probably train a model, I should come up with an algorithm that is actually able to solve the typo problem as well, or something like that. So unless you go back and really explain what's going on, you may not be able to fully improve your algorithm, and you may end up having unexpected wrong predictions. So again, we come back to the same problem. If we have these all issues, trust, regulations, these example mistakes that I provided, that black box algorithm may not satisfy, doesn't we have to go for the white box, transparent models? Or it still means we can stick to the black box algorithm? So this is really a trade-off, because if you have black box algorithm which you cannot explain, it means it can have unexpected errors. But if you have a white box algorithm, it means it is transparent, you maybe fully know what's going on, excellent, but it may be a bad algorithm. So you know what goes on behind, you know why your algorithm is making this or that prediction, but it is actually making them wrong. So if it is not accurate model, do you really need to know why this or that prediction is made? So this is a really trade-off which explainable AI solves by kind of opening the box, okay? So it says, instead of trying to choose between white box or black box, go on and choose the black box and then open the box and see what's going on inside. So explainable AI is a family of methods and techniques that are basically helping you to kind of take this black box and open it to see what's going on inside. Okay, so they help you to understand what are the patterns that your model captured, what are the reasons behind this or that predictions that your model is making. Again, coming back to this trade-off, we said that interpretability or explainability goes down when you use more and more complex models like the black box models. So what explainable AI techniques are trying to do is they are trying to kind of convert this graph into this type of graph. So they are trying to keep the interpretability level to satisfactory level, or the same level, or at least a level which you can accept, but instead increase accuracy. So whenever you apply more and more complex models, you have more and more accuracy, but you don't lose interpretability. That's what explainable AI gives you. So it gives you the ability to have larger set of applications for complex models than they would have if explainability didn't exist. In general, explainable AI is actually called XAI. X stands for the second letter of explainability. So XAI is explainable AI. And in general, there are two types of explainable AI. One are the ones that provide global explanations. So in general, you are trying to understand how good your model is, like in general, fully. And the second part is when they provide local explanations, when they tell you why a single certain prediction was made. Let's say you have a lot of customers and you want to predict whether these customers will accept your marketing offer or not. Global explanations will tell you what are the most important factors that help your model to make this prediction. Local explanations will tell you what are the individual important factors that resulted in a certain prediction for a single customer. So if you do that really for a single customer's individual expectation, you can do the same thing for a group of customers, like individually explaining 10 or 20 customers, then or customers in a single segment. It will be again local explanation, but group-wise. We will talk about both of them today. So we will go over examples of global explanations, and we will go over examples of local explanations to see how they differ. In general, I always separate types of machine learning algorithms in terms of source data. So my favorite type is called tabular data. Whenever you have these data in terms of rows and columns, like the databases, like the Excel tables, okay? But it's small or big, doesn't matter, right? But I like whenever I have data in tabular basis. The reason I like it is because most of the business data, like 80–90%, I don't have correct statistics, but around 80–90% is tabular data. Most of the business problems are problems related to tabular data. Like if it is about your customers, then you don't really most of the time have image of your customer. Many times you have the customer characteristics like name, surname, the country of residence, the maybe age and gender, I don't know. So you usually have data in tabular format. We will see that in a minute, but in general, whenever your data is in tabular format, local explanation is not really very useful. What is more times useful is global explanation. So if you have tabular data, like imagine you have 6 million customers, 50 million customers, you cannot really go on and locally explain each of them. So most of the time you go on and use global explanations for tabular data sets. But if you're dealing with problems in the field of computer vision or natural language processing or related, let's say you're running some image classification tasks that are classifying cats and dogs or stuff like that, then you cannot really go to global explanation. The problem is for global explanations, you have features like we discussed, the age of the customer, the country of residence of the customers, and similar other features about customers. When we go to the image classification task, what you have is an image. So all of your data is inside one image. You don't have like many different features. All of the features are extracted from that one single image. So you cannot really do any global explanation in that case. Well, you can do, but it's not really very useful. So what you stick to in case of images most of the time or text is local explanation, trying to understand from each single image why a certain prediction was made, and we will try to do that together. In terms of global explanations, we have many different approaches, but most of the time, those are the two approaches that are applied. One is feature summary. I bet that those of you who have been working with machine learning previously know about these so-called relative importances. So when you're running, let's say, a decision tree algorithm or similar other algorithm, and you want to see what's going on behind, you're actually checking the relative importances to see how much each variable is important. You cannot do that for images, because for images, the features are actually extracted inside the network of, let's say, neural network itself. So you go on and check relative importances for decision tree. For models like the logistic regression, linear regression, so more older and simpler models, most of the time, you have absolute importance. So you don't only say how much relatively this or that feature is important. You can actually give a quantitative value and say, you know, this is how much important this single feature is. Like in absolute values, not just compared to other features. In general, this is how important it is for the problem. For some models, you can even get the direction of effects. So sometimes you say, you know, gender is important, but I don't know whether males churn more than females or vice versa. Sometimes you can actually understand the direction of effect, and we will see the example today. But those are like summary statistics, summarized overview of how important your feature is. It is very useful for having explainable AI to actually visualize your features. And there are many ways to do that. And the two most important ones, probably, which I mentioned here, are PDP and ICE, partial dependency plot and individual conditional expectation plots, which we will see a bit later on. Let's go on and start from the relative importances. Oh, sorry. Before going on, let's discuss overall ecosystem. Okay. So if you want to apply explainable AI, if you believe that you should actually have an algorithm that you can trust, you should have an algorithm that meets regulatory restrictions of being explainable. You should have an algorithm that should give you actionable insights. Then one approach is go on and apply models that are inherently explainable. Those models are GLMs, general linear models, or GAM, general additive models. Those models inherently explainable, so they can fully tell you why this or that predictions are made. So they're fully white box. And these white box models actually have experienced some improvements during the last years as well. For example, in 2013, which was 7 years ago, there was a paper published called GA2Ms, which is like GAMs, the same model I was talking about. It's very old model, but more powerful. In statistical terms, it actually takes into account for interaction terms as well. So these models that are white box, this is like one area of research. People are trying to take white box models, which are interpretable, and make them more accurate. Second area of research is taking black box models, which are accurate, make them interpretable. So it's like you have the two edges. Some models are trying to take this edge, which is interpretable but not accurate, and bring them here. Some of the algorithms are trying to take accurate model and bring them here, make them interpretable. I like the second ones mostly, and we'll keep our attention on the second ones, but it's also important to know that there are algorithms that are strong enough to be accurate and to be also explainable. This GA2M is one of them. Microsoft actually published a recent paper 2 years ago, if I'm not mistaken, and they use the same algorithm, but they call it EBM, Explainable Boosting Machine. So if you have been running machine learning algorithms, or if you have been checking some solutions in Kaggle or similar websites, you probably have seen that gradient boosting machines are always the winner's algorithm, or at least most of the time. So what Microsoft is doing, it is basically using this algorithm, calling it boosting machines because it's strong, but explainable boosting machines because it is very explainable. They even have their own package, which is running explainable boosting machines. And most of the time, it is able to kind of compete with the main strongest algorithm that we have for tabular data, like XGBoost or LightGBM, and at the same time being fully explainable because it's based on GAMs, general additive models. Another set of algorithms that we know very well are decision trees that are most of the time very explainable, not fully explainable, but very explainable. So this first line, explainable models, are the models that are kind of already explainable, and people are researching to make them more and more powerful. The others are the models that kind of try to make black box explained. So one of the approaches is SHOP. SHOP is quite a recent approach. If I'm not mistaken, the paper by Lundberg et al. Was published 3 years ago in 2017, where they provided a uniform approach based on game theory that is able to do local and global interpretations. So whatever we just discussed here, local and global, SHOP is able to do both of them. It's very strong, and this is usually the first thing we are running behind to use whenever we need to give an explanation for our algorithms. The second one is LIME. LIME is like older approach. It stands for, it is actually running local interpretation. And in behind, it is running like explainable models that are approximating the black box models. For example, we have a very accurate model that is able to predict car prices, but it is black box. You don't know why certain cars have higher price than others, and you want to understand that. What LIME is doing, it is taking your black box models that are very accurate, and they take a lot of inputs, like a lot of features, and make a prediction about the car, giving you some output. So these black box models are actually trying to, this LIME is actually trying to take the prediction of black box models and approximate it. So try to develop a small linear model for some subset of data, let's say for only Toyota cars, or for only Volkswagen cars, for only small part of the cars, not for all the cars, and try to explain it for these cars only. That's why it's called local. Then if you want to understand why BMW cars are expensive or not, LIME will actually take only these BMW cars, only this local part, and try to explain them separately. So the idea behind LIME is that if white box algorithm is not strong enough to provide good accuracy, use black box algorithm and then select some parts of your data that individually can be used white box algorithm for to provide high quality of interpretations and also accuracy. And the last one are rule fit. The idea behind these rule fit algorithms is that many people say that human being understands rules better than anything else. So in behind, we are trying to kind of in our brain use rules and comparisons and analogs to interpret or explain stuff. So we are trying to say, in comparison to this is better. In comparison to this feature is better. In comparison to Toyota, BMW is more or less expensive. In comparison to these customers, the following customer will or will not churn. So human brain is working like rules most of the time. So our brain understands things easier if we kind of get them represented as rules. So rule-fit algorithms are a family of algorithms that are trying to extract rules from the data. Most of the time, these rules are very useful, but they're really used for interpretation only. So you cannot really use this algorithm to make a prediction because they will extract quite important rules, but in general, algorithms will not be high quality enough in terms of accuracy. So they may give you 1, 2, 3 good rules, but they will not be competitive to the black box models. In my experience, what I'm usually doing, we are trying to run in metric explainable models. If they're not enough, we are going to black box models and explaining them using SHAP. If they're running this algorithm for tabular data, if it is like images or whatever, we will go to line. But if you're doing that on tabular data, we are always using SHAP because SHAP is able to provide global interpretation. And many times we are also running rule fit in behind to get 1 or 2 rules, so that whenever we meet with the client and client asks why your model is doing a certain prediction, we will say, you know, if this is higher than this and lower than this, then the model says that this is the prediction, and the client is able to understand better because of the same thing I mentioned, because our brain are able to consume rules easier. So this is not a very high quality picture, but let's take a look. So this is the first example I want to discuss with you. This is probably the most popular plot you can see in any machine learning project that is trying to interpret the results. This is called relative importances of features. Okay, so it is done on a very famous data set of Titanic. So you know the Titanic ship which crashed, and at least in the movie, Leonardo DiCaprio died and saved the woman, but he died. So this is the data set of the real Titanic crash and the people who died or survived. So this is very famous in the field of machine learning. A lot of people are playing with this data set to learn different models, and the overall goal, the overall objective is to try to predict whether a certain person with a certain characteristics will actually die or will survive Titanic crash. So we have the titles of these people, Mr., Mrs., or whatever, Doctor, Sir. We have the gender, we have the fare, whether it's the low fare ticket, middle fare, or high fare ticket. We have their age, and so on and so forth, whether they have siblings together, whether they have spouse. So we have a lot of variables in this data set, and we are trying to predict whether they will actually survive the Titanic crash or not, given the historical data. And if you run it, you can see that the survival basically depends most of the time on these top features that are, for example, gender. So you can see that gender plays an important role. Like whether you are male or female, it really plays a role. It really played a role in case of Titanic survival. Okay, so this is already explanation. Okay, this is not interpretable AI, but this is explainable AI. The reason this is explainable is because you know why. You know why your model gives certain prediction for Leonardo DiCaprio guy. Because of his gender, because of his age, not really because of these last features, because they are not very important. Most of the time because his gender, because of his age, not really because whether he has siblings or not. So you know that those are the information that played important role. What does it help you to do? If you were collecting this data and it cost you money to collect this data, let's say you had to have a survey or something like that, then in future you will not collect data on these not important features, you will just collect data on the top important ones, if they are enough for you. So this really helps you to understand what's going on behind, why your model is predicting that a certain passenger will die or not. But this is just explainable AI. It is not interpretable AI. Why? Because interpretable AI asks the question, what if? What if I don't know, Leonardo DiCaprio was younger? Would he survive or not? I don't know. Because I know that age is important, but I don't know how age affects. So even so, I have explanation behind the prediction. A certain prediction was made for this guy because he was young, because of his age, because of his gender, but you don't really have the detailed explanation or interpretation. What would happen if he had like lower age or higher age? What if he bought another ticket? What if his ticket was like higher class? Does it mean that he would be closer to the entrance or exit and he would be able to leave the ship sooner? We don't know that. So we have kind of the superficial explanations, but we cannot go deep into the what if analysis by just looking at these summary statistics. This is when this shop is coming in, okay? So this is example of global interpretation because it is not for just Leonardo DiCaprio or the other guys. It is just for in total, like gender or age is important in terms of prediction for the model, for all the passengers. It is not individual, it's global. But still, it is just explanation, not interpretation. But SHOP, fortunately, helps us to go deeper and provide interpretation. So SHOP gives you something called a Shapley value, or SHOP value as they call it, which if higher, it means probability of survival is higher, okay? So if SHOP value, you can see SHOP value on the horizontal axis. See, it is negative on the left-hand side, 0 here, and positive on the right-hand side. If SHOP value is higher, it means probability of survival is higher. So whatever we have on the right-hand side means probability of survival is higher. Whatever we have on the left-hand side means probability of survival is lower, okay? This is a bit confusing graph, so if you're not familiar with it, let's draw a bit more attention to it. This color bar shows the value of the feature. So if you go to the age, for example, the purplish or reddish value color means higher age, and the bluish color means lower age, because we speak about age here. So because bluish color is here, it means those who have a lower age have higher probability of survival. And those who have higher age, so it is purplish, they're like negative in terms of SHOP value, which means they have lower probability of survival. If you go back and think for a minute, this is quite intuitive, right? Probably the children were actually rescued first, and at the same time, the older people probably were not so mobile. They couldn't really make it out of the Titanic, and maybe they also left the children to take their place. So this seems to be quite intuitive for me. Gender, if I'm not mistaken, is encoded 1 for males and 0 for females. So those are the two values we have in the data set. So high gender means male. Low gender in this data set means female, which are just placeholder values. What you can see from this plot that SHOP is providing us is that people who have high gender, which is people who are males, females, 1 is female, 0 is male, people who are females have higher probability of survival, okay? So females have higher probability of survival and males have lower probability of survival. Let's go back. This is the general summary statistics of the feature. It doesn't tell you anything about how gender affects. You know that gender is important, it affects survival, you don't know how. But do males survive? Does male survive longer than females? If I'm a male, do I have higher probability of survival than females? We don't know. But this plot actually tells us that, you know, females, the purplish ones, are more probable to survive. And we have seen it in the movie, right? This Leonardo DiCaprio guy was saving the lady and dying himself. I think this movie is counterintuitive. I was always thinking that he could actually survive himself as well, but anyway. So they probably tried to make it more romantic. So as you can see, SHOP is helping us to have deeper explanation. And in this case, help us to have the kind of what-if analysis, to have interpretable model. So in this case, this is an insight. This is not actionable insight. You cannot say, what if I change the gender of this guy? Obviously, you cannot do that. But there's something that you can change. Well, what if these guys had higher or lower fear? What if, or I don't know, what if the class of this passenger was different? So a lot of things that you can affect and a lot of things that you can change, you will get insight on them as well, okay? So in this case, you can now, when somebody asks, do the males survive more than females? You will say no, because you have this information. But just taking a look at this plot, you wouldn't be able to do that. So explainable AI helps you to overall explain what's going on behind the algorithm, whether it's white box or black box. And this shop is so beautiful that it is not just explanation, it is interpretation itself. So you can use it as a what if analysis tool and understand what will happen if you, in case being able, change and take some action. Let's say this was not Titanic data, it was marketing data. What if you concentrated on male more than female customers? Or what if you concentrated on both of them equally? Or what if you concentrated on some customer segment more or less? You can get the answer to what if just because you have interpretation. Let's go to this example. So as you can see here, we know how gender affects, but if you have a numerical variable like age, it's really difficult to make sense of this sharp plot. As you can see, lower age people have higher probability of survival. Middle-aged people, like some of them survive, some of them no, they're closer to zero, and high-age people usually don't survive. And similarly, you can have interpretation for other variables like fear. See, for example, fear, when fear is low, they have the low fear ticket, and it almost doesn't affect the probability of survival. It's very close to zero. But people who have higher fear, like purplish ones, have higher probability of survival. In order to have better interpretation than this plot provides, you can go on and individually plot the features. This plot is called partial dependency plot. Okay, so this yellow guy is the PDP, partial dependency plot. These guys here are actually like extension of partial dependency plots. They are called individual conditional expectation plots, but let's forget about them. The most important one is this yellow guy, partial dependency plot. So this yellow guy shows, in average, how the values of your feature affect the prediction. Their prediction probability here. So zero means that zero sharp values and no effect. High values means higher probability of survival. As you can see, once the value of fair, this is fair, that I was showing you here. Once the value of fair is increasing, in the beginning, it doesn't really anyhow, it is horizontal line. It doesn't really anyhow affect survival. But then in the end, it actually affects very positively. So if it is the very, very high fare, imagine it's like the price of the tickets they bought. If the tickets they bought was very cheap or middle ticket, it doesn't really affect the predictions. As they survive, don't survive, it doesn't really matter. But if you use a ticket that is very expensive, probably like VIP rooms or whatever, probably they had the access to exit in the very beginning, so they were able to actually leave much sooner. So as you can see, the higher values of fare have positive effect on the probability of survival, which you could see here as well. See, the very high values have like outlier positive effect. This is called partial dependency plot. Okay, this is called partial dependency plot. The way you get this plot is basically making prediction using your model for all the possible fares. So you say Leonardo DiCaprio, who is male, who is this year's old, so you have all the information about him, like all these features, and you say, what if he didn't have this low fare, because you remember from the movie he had the lowest possible fare. What if he had a bit higher fare, like the middle priced fare? You will see that still he would die. What if he had a bit higher fare? He would still die. What if he had very, very high fare? He would survive. Okay, so of course this is very artificial example because it's about Titanic crash, but similarly in business, you can say, what if my customers are more exposed to marketing? Would they really buy? So you can identify not only whether marketing is important in terms of getting more and more customers to your business, you can actually understand which type of marketing, and you can understand how much money you should invest in marketing. Is this much investment is enough? Like if this was about marketing, you could see that lower amount of marketing doesn't really help. Middle amount of marketing investment doesn't really help. High amount of marketing investment will actually drive your customers to your business. So this helps you not only to identify whether or not a given feature is important, you can actually go on and understand whether the actions you will take in order to have better business values, better business output, should be in this range or that range. So this is the perfect what-if analysis tool that you can use. Okay. Now let's forget the tabular data. Let's say you have images. One of the most popular tasks in the field of image classification are implemented on this so-called MNIST database. If you have ever tried to, I don't know, learn computer vision or try to classify images, probably the two most important and popular tasks you have seen in the beginning was identifying handwritten digits. So we have digits from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which are handwritten. And they are developing algorithm to recognize this. So if somebody puts this, is it 2 or 3, is it 9 or whatever, to recognize handwritten digits. And the second probably most popular task, which people in the beginning usually try to accomplish for learning computer vision or machine learning or deep learning with images, is classifying cats and dogs. Okay, whether you have cat in this picture or dog in this picture, or whether if you have both cat and dog, which one is cat, which one is dog. So we'll try to speak both of the examples and try to interpret them. Usually these kind of tasks are carried out by so-called neural network algorithms. Neural networks are one of the most kind of coolest algorithms nowadays. Everybody's talking about them. And they're very complex, and it's very hard to understand what they're actually doing. So this shop is actually able to explain what neural networks are doing as well. To say the truth, we have to give the credits to the guys who invented an algorithm called deep lift. So deep lift is an algorithm which is able to understand the effect of different types of picture on the output, different features of the picture, like why the certain picture was classified as 2. Is it because of these pixels or the bottom pixels or the middle pixels? So deep lift is a very nice algorithm that helps you to do that. And SHAP is basically built on deep lift as well. And they are trying to help you to understand which parts of the image, which pixels, which features of the image are the reason why your algorithm classified them as something that it was classified. Why did you receive the following output? So this is a typical output that you will see if you implement SHAP. I'm not showing any code here. I'm not trying to go into technical because code is secondary. It's very easy, just 1 or 2 lines of code. So I'm sure if any of you want to implement this, if they're familiar with Python or R, they could really go and implement SHAP because these algorithms, neural networks are much harder than running the SHAP code. So the key part here is the intuition, then you can use them. So because we are talking about images, because we are not talking about, let's say, customer data with different features like age, gender, or Titanic data where we have sex, where we have passenger class. In Titanic data, because we have all these issues, we interpret separately age, separately sex, separately fare. But here we have a single picture of a handwritten digit. So we cannot really separately interpret parts of that image. Instead, what we are doing here, we are going to local explanations. So we cannot say globally for all the images, the top part is the most important part in terms of classification. No, because maybe for classifying for the top part is not important because top part is empty here. So maybe important part is this part, I don't know. Maybe for 2 important part is this curvature here to classify whether it's true or not. Maybe to classify whether a certain image is 1 or not, the important thing is whether we have something else here or it is just vertical. So it's like left or right parts, not the top or bottom parts. So you cannot really have global explanations for images that is very useful because you may have very, very different images. And because you don't extract features for images yourself, algorithm itself is trying to find these patterns, like neural networks, convolution neural networks or stuff. So what SHAP is doing, it is trying to provide local explanations here. For example, it takes this one image, which as a human we can clearly see is 2, and model predicts it as 2 or maybe something else. So SHAP shows you all the possible images. It's very transparent, so probably you don't see it very well, but we have all the images here in the backside. So we have 0 here, see? 0, it's very transparent, but we have 0 here. So this is position for 0. What SHAP is doing, it is basically putting 2 over 0. And trying to see like the intersection of these both pixels of these both photos, okay, how much they intersect. As you can see, 2 and 0 intersect a lot in this top part because both of them have this curvature. but they don't intersect in this part because 0 is empty inside the circle and 2 is not, right? Then we have 1 here, 2 here, 3 here, 4 here, 5, 6. You can see 6 better, see? So this is 6. So this is position for 6, 7, 8, 9, 10, and 9. No 10, sorry. We have only digits. So what SHOP is doing, it is basically putting all the possible outcomes. All the possible outcomes are digits from 0 to 9 in the backside. And it is putting the real value on it as well. The real value is 2. So real value is overlapping. And it is basically shows why a certain prediction was made. So you can see that we have the colorful part here. As discussed, the positive colors, in this case, it's SHOP value. So this purplish color means very positive output. So basically very high and correct probability of being 2. And the negative values means very high negative values. So basically the values which helped you to decrease the probability of being certain digit. For example, 9 is actually a better example. So let's go to 4, sorry. So we have 4 here. 0, 1, 2, 3, 4. So this should be the real value. As you can see, because this is the real value, you have a lot of overlap here. So the 4 overlaps with 4, and because you have empty part here, see, you have an empty part in behind in real 4, and you have empty part in this handwritten digit as well. So because this empty part intersects, both of them have empty part, unlike 0, 0 is not empty in the top, see? So because both of them have empty parts, it is colored purplish. So basically SHOP is trying to tell you this empty part is where we have overlap of same pixels. We have empty parts in the possible outcome and in the real outcome. And because we have this empty part, it basically provides us very, very high confidence. That's why it's purplish, of being 2. So purplish means high and positive. 4, sorry. Similarly, if you go to 9, see, 9 has this top part, right? It is not empty. Like in real 9, you have this top part. So the top part doesn't coincide with the top part of 4 because it is empty. The reason this doesn't coincide is the reason why we don't predict 9. Why we don't predict this to be 9? Because, I mean, the rest is the same. Like, if we had the top part, it would very much be very similar to 9, right? The reason this is not 9 is because we don't have the top part. So it shows not only the reason why we have predicted it correctly as being 4, it also shows the reason why it correctly predicted not 9. So this part, this top part, is the part which helped, which is blue, so which helped to decrease the probability of 4 being 9. So the probability of being 9 is decreased. That's why it is blue. Why? Because 9 has the top part which 4 doesn't have. See, for example, for 1. Why we predicted 1 here? Because 1 is the only one which has like the exact vertical line. Others do not have exact vertical line. For example, for 0, it is empty. For 2, it is not very vertical. It is curvature here. And because we also have empty parts here, empty pixels. So for 2, we don't have empty here. We have this curvature. For 4, we don't have empty. But for 1, we have empty parts. So not only the existing black pixels coincide, but the empty white pixels coincide as well. That's why we have this prediction. Last but not least, for zeros, why we classify this guy as 0? Because 0 is the only one with overlaps with the circle and with the overlap and with the empty part inside the circle. For example, see, here we have 6. 6 is very close to being a circle, right? It's very similar to being 0. So it's like a circle as well. So we could really end up having 6, but the difference is that 6 has this top part, which is like jumping above the 0 circle, and this top part is the reason why it was not classified as 0. Okay. So SHOP basically helps you to understand what are the components of the image, what are the features of individual image in this case, that were the reason why a certain image was classified as 4 or 0. Now let's go better, more intuitive example. Cats and dogs. But in order to be able to not fix on SHOP too much, I provided the example of lime in this case. So SHOP would be able to do the same thing, but in this case, I'm providing the example of lime. So in this case, we are trying to predict whether we have whether we have cat or dog. Okay, so cat is 1, dog is 0. Okay, so cat is green and dog is red. So the reason this guy is considered to be cat, as a human we can see it is a cat. So why do you think this is a cat? If you ask a human being, probably human will say, I mean, this is cat. I don't know why exactly. Maybe it's because of ears. So cat has these triangle type ears, right? Which dogs do not have. Dogs' ears are more like concave. Cat's ears are convex. The cat has like tail, which is, I don't know. You may understand that this is cat because of tail. It has this nose, and then it has the mouth, which is a bit different than for the dog. So there are many different reasons why, as a human, we understand and differentiate cats from dogs. But what our algorithm finds, Lime tells us that the reason this is cat is because of the overall body. It's not because of really this this part of the head, not because of eyes, but yes, it is because of the mouth, because of the nose. It is a bit because of tail, but not fully. You see, the last part of the tail didn't really play a role. So you understand that if a cat had a different last part of the tail, let's say if you put, I don't know, some people are putting clothes on their animals, right? So if you put, I don't know, some bantik or something like that, or some clothes on the last part of the tail of your cat, it doesn't really affect. Okay, so if you like do something with this last part of the tail, I don't know, you put some clothes on it or whatever, it will still be recognized as cat because this doesn't affect the prediction. Okay, this is important. You know what affects the prediction or not. Similarly, this was identified to be a dog because of the face, not because what you see here in this part of the dog. Why is this important? Because if you put something on your dog, I mean, some people are putting these things to individualize their dog, like dog name or contact information of the owner of the dog, so that whenever dog is lost, they can contact him or her. It will not affect your predictions. Why? Because the most important part is just mouth, nose, eyes, forehead, and the rest are not really important. We can see that ears are not important as well. So you know that some people are actually cutting ears of the dogs so that whenever they get into the fight, their ears do not become vulnerable. I don't like this at all, but we know that this exists a lot. So you know that you can see from here that ears do not really affect the prediction. So whether you have dog with long ears or cutted ears, they will still be recognized as dog. This is what you can see from this, okay? So this helps you to understand where your model is making a prediction and why a certain prediction was made. This is very important because in the era of coronavirus, I mean, nowadays everybody has to at least mention coronavirus at least once, right? During the presentation, so I don't want to be an outlier. In the era of coronavirus, we are wearing these face masks to be safer. Assuming we are safer when we put these face masks, the iPhone face recognition is not working with the face mask. At least up until recently, it was not working with the face mask. You know why? Because if you try to interpret the face verification algorithm of iPhone, you will see that the mouse is important. It's not only eyes. So if Apple was able to come up with an algorithm that eyes were enough, or the top part was not enough to recognize the certain person and verify his identity or her identity, then mask wouldn't really create any difference. But because mouth, nose, and this part of the face in general is important, that's why the iPhone face verification is actually not working whenever you have a mask, because it cannot see this part of your face. So whenever you explain algorithm, you can understand when it will and when it will not work. And you don't have to wait the unexpected situation like coronavirus and face masks to come into life to understand that they will affect your predictions. Because if you have the explanation, you will always know that these parts are important. So when people start to wear something on this part, you know that your prediction will actually not be useful anymore. So explanation can be really important in terms of taking your actions in the future. Okay, so let's go on and discuss some stuff about XAI, explainable AI. Okay, so we discussed that explanation is important. So I assume at least most of you, but I hope all of you agree that explainable AI is like a very key topic in order to have trust in AI, in order not to have unexpected errors, and sometimes just to be able to run the algorithm because of regulatory requirements. And I bet that if you agree with me, then most of the time you agree because it's very important to have actionable insight. But let's see what are the drawbacks, what are the limitations. So we spoke about the good. Let's now speak about the bad and the ugly. Okay, let's start from the bad. Does explainable AI help us to identify real patterns in the data? As you noticed, Sharp, Lime, or any other method that we can talk about, all of them help us to understand what our algorithms found. So what are the patterns that our algorithms found from these images or from Titanic data? What are the reasons why our algorithms are making the prediction? So all these explanations are model-based. They're based on our models. And when we say they explain or interpret, they actually explain the model, not the reality, the model, okay? So your explanations are as good as your model is. If you have a bad model, you will obviously end up having not the best explanations possible. Sometimes maybe like an average model is enough to find the explanation, but most of the time your explanations are as good as your model is. So the question is, does explainable AI help to identify real patterns in data? Yes and no. Yes, because if you have a good model which was able to capture a lot of real patterns, you will be able to identify them using explainable AI like Sharp and things like that. But if you don't have a good model, then explainable AI will actually explain the patterns you have in your model, not the pattern that exists in reality. So if your model is bad, if it actually captured wrong patterns, you will be explaining wrong patterns. Okay, so this is very important. Don't just jump into conclusions by just taking a look to explanations and say, this is what is important. No, this is what is important for your model. It doesn't mean this is what is important in reality. Maybe in reality, having the tail identified as important feature could be the key of having better model, but your algorithm didn't learn it. We don't know that, okay? So explainable AI nowadays is, well, before it was model specific. People were trying to explain each model separately. Now things like Sharp, for example, I wrote it here, are model agnostic most of the time. So they explain any model, okay? So whether it's logistic regression or decision tree or neural network, you get same type of explanation. So it's uniform, which makes our life easier to explain the stuff. So they're like model agnostic. You can use it for different models. Still, they depend on your predictions, okay? I was working as the head of data science team at a company that was in the health tech sector. So we were analyzing a lot of clinical data. And we were using only classical statistical models. We were not at all using the complex machine learning algorithms. Some of the classical methods we were using, like the traditional statistics, were much more complex than the machine learning algorithms we could use in terms of implementation. But still, we had to stick to them because we should have had clear explanations. So we should have had white box models, because in the clinical sector, we are dealing with the health of patients. We cannot really say my algorithm is predicting that this guy is healthy or that guy will die. You cannot do that. You have to explain why, because this is very important. Sometimes we are using AI in fields where our predictions are like critically important and can change lives. And we cannot just say, I have black box algorithm, it's very accurate, just go on and trust it. You have to explain it. That's why like places like Food and Drug Administration in US, FDA wouldn't really accept if you submit perfect analysis using black box models without explanation. So we were stick to the classical models. But you know what we were doing? Even we were using white box models, when we were providing explanations, we were not doing that on model-based basis. What we were doing, if we identified that, let's say, gender is important, we will go back to the data and just use simple old descriptive statistics, summary statistics, to see whether really the proportion of males and proportion of females, like simple hypothesis test or things like that, where the proportion of males and females are really different in terms of survival. So is really gender affecting? This is very important, because if you go back to the data, you're able to find patterns in the data, because all these models and methods that we are discussing, they're able to explain the patterns that your model found, but not the patterns that really exist. Sometimes the patterns that model found are correct, but sometimes some of them are not really correct. Your model, because of some outliers, can really find a noisy pattern. So you don't want just say that this is the pattern that is the reality. You want to go back to your data and explain. So sometimes, in order to identify a real pattern, you should use explainable AI to find the possible patterns that the model learned. And then you have to challenge them by going to summary statistics, by going to your data and trying to calculate averages, median, simple stuff like that. Just plotting scatter plot or stuff like that to understand whether this pattern that my model found really existing in the data. So if this is the pattern that my model found, this is really the pattern I have? So are the middle fare passengers of the Titanic having the same survival rate as the lower fare? I mean, according to the model, yes. But is this the reality? I don't know. You have to go back and check. If you have a perfect model, probably yes. You will never harm yourself if you go and do one more step and check it from the data, okay? Second thing which I want to discuss is so-called causality problem. Probably one of the first things we learned from the statistical classes or econometrics or data science or similar courses from university or online courses, training centers, is that correlation does not imply causation, right? So this is like kind of the first rule we have in statistics probably that we cover. Usually what I do, I ask my students like what correlation is not, and their answer is causality. So correlation does not imply causality, right? It may or may not be causality. So like correlation is bigger set and causality is just subset of correlation. So the question is, does XAI, explainable AI, help to identify causality? As I said, causality is subset of correlation. And it's important to keep in mind that all the machine learning algorithms, or at least let me just for safety say most of them, but I think all of them are designed to capture correlation, not really causality. So what they do, they really tell you whether you have patterns on your data or not. They don't really say this feature A caused the outcome B. So you don't really capture causality, you capture a pattern, a correlation, okay? So whether it helps you to identify causality, well, as I said, causality is a subset of correlation. So in order to identify causality, you should have correlation in the beginning, right? And explainable AI helps you learn what patterns are identified. So the answer is yes. Explainable AI helps you to capture causality because it helps you to identify correlation, and then you can use it to identify causality. But the answer is also no, because it doesn't really tell you whether you have causality or not. So it's very common. Even all of us may know that correlation does not imply causality. I'm pretty sure at least once all of us in our lifetimes probably made that mistake of interpreting correlation as a causality. At least I'm doing it a lot. Okay, so because our brain is biased, so our brain is always trying to find causal connections. Even so you can be an excellent expert, you can still be misled by your brain. So, for example, we see that people who have higher fare have higher probability of surviving. But is it because of fear? Or maybe the people who have like the VIP fare are mostly the, I don't know, are mostly the people who have younger or the people who are females. And we already know that being younger or being a female affects positively. So maybe fear doesn't really directly affect, it has indirect effect to probability of survival. So whenever you use AI models, all of them are trying to find patterns, but they are not able to give you the root and cause of the pattern. Okay? They don't tell you that this is the cause and this is the effect. This is the variable and it causes this. You know that survival rate and fear are related, but you cannot really say that survival is caused because of fear. Maybe fear is affecting something else, which is affecting survival rate. This is a very favorable problem in statistics, and it is important to understand that explainable AI is making our life easier, but by explaining patterns found by the model, so that then we can sit down with a team of experts and try to brainstorm and understand whether these patterns are causal patterns or not. But directly, it doesn't really tell us whether we are observing causality or not. Okay, so it doesn't really, it is not really yet designed to capture causality. Fortunately, there's a lot of research going on now on causality, trying to, I don't know, somehow capture it. But up to now, there is no method which I can tell, let's say, go and use ABC method. If you capture causality, and you will have no problem at all, okay? Unfortunately, there's no way to do that up until now. There are methods that help you to design an experiment so that you check whether you have causality or not. Check, but not to go on data and find causality directly, okay? So this is the ugly part. So even so, explainable AI is kind of an excellent topic, and I think this is the most trendy topic nowadays, one of the most trendy topics in the field of AI. It still has drawbacks. Drawbacks of first explaining the models, not really the patterns in the data, but the patterns in the data that were actually found. Simply because if you couldn't find the patterns, you cannot explain them as well. And second, because they're explaining the model and model is finding only patterns and causal relationship, they are not really helping to, they're assisting, but not really fully helping to identify causality. Those two things create the possibility for future research lines, which a lot of people now conduct research on, and I myself am very interested in we are trying to conduct research on this as well. So we are able to solve problem one issue. The tabular, our AutoML that I was talking about, that we have a metric at my company, it actually tries to solve the issue number one. But causality is an issue that nowadays, at least I don't have any solution in my mind. And I think nobody in the world has like clear-cut solution how you can just have an algorithm automatically go on and identify causal patterns. In the end, let me just provide you several references for those for whom this topic was interesting. Quick reminder that explainable AI and interpretable AI are many times used interchangeably, but they are not the same thing. Just a quick reminder how they differ. If we go to the decision tree, like we discussed, for example, these feature importances, this helps you to explain why a certain prediction was made. But you don't really have the what-if analysis tool. You cannot really make the prediction yourself in future, right? So to do that, what you can have is, and many people know this decision tree graph. For example, decision tree graph, the graph you get after running the decision tree model, this is already making the tree interpretable. Because when you see the tree, you can already see why a certain prediction was made. Not because a certain feature was important, but you can see which values of that feature played a role. So you can understand the overall path to the prediction. So just keep in mind that interpretation and explanation are different things. And you can interpret the model without explaining it, or you can explain the model without interpreting it. Most of the time, even so we call the field explainable AI, you want to do interpretation, okay? And these references I provide are actually quite nice references that will help you to go into interpretable or explainable AI. First one is a very nice free book published on GitHub by Christopher Molnar called Interpretable ML. So Interpretable ML. This is the book by Christopher Molnar. So this book covers quite nicely or most of the existing techniques of different and the different models and approaches that you can use for interpretation, and it is very updated. So Mr. Molnar is going and updating it a lot, and it has also some R codes. Unfortunately, not Python codes, he said, but that's not a problem. It doesn't really mention fully the drawbacks of different approaches, but there is another book coming up by Molnar, which is actually explaining the drawbacks of the models as well. The other three are just hyperlinks to the packages that I used as examples for this slide. So I use Lime for cats and dogs. You can go on and check it. I use Sharp for the handwritten digit explanation and for the summary plot. And I use PDP box, and the name suggests PDP, partial dependency plot box, in order to get this plot. So we have hyperlinks here that you can go on and check them out in future. Okay. So that was all what I planned for the presentation. Thank you very much. I hope this was interesting to you, and I will be happy to talk about explainable AI in more detail. So this presentation intended to be more like generalistic, but if there are people who are interested, we can go on and talk afterwards, maybe someday schedule another call to discuss the math behind and the potential research topic. Thank you very much, and let me know if you have any questions to discuss.
Thank you, Hrant. It was very interesting and informative session. Thank you for your time and presentation. So if anyone has question, please write your question in Zoom group chat, or so there goes one question. Can you read, or should I?
Yes, I do read. So we have a very nice question. It is asking whether we are able to interpret the model layer-wise and understand which layers are important. The examples I discussed, not really. But in general, there exist the possible approaches which help you to kind of get the heat map of the, I think you're speaking about neural net. Yes, convolution neural net. So there are techniques that help you to understand which nodes are actually firing and which nodes are actually used for certain features. Actually, DeepLift is able to do that as well, which is behind the shop. I think shop itself is not doing it. But DeepLift, the package used behind the shop, is actually able to do that. So you can basically get your layers and try to provide interpretation layer-wise to understand which are the parts that are responsible for a given feature as well. So the answer is yes. In general, you can do that, but not with the presented examples.